Hey guys, welcome back for our 12th episode in the AP review series. And in this lesson, we're going to take a look at some different integral applications. We'll call this part one of three. I'm going to split this up into three parts with some various integral applications that are going to be important not only this year, but in every year on your AP exam. So I want to begin today looking at motion along the line. So we're going to take a look back at particle motion. If you remember, a little while back, we did this on the derivative side of things, dealing with position, velocity, and acceleration, talking about taking the derivative to go down. And then today we're going to look at heading back up through integration and antiderivatives. But I want to begin graphically because I think that that's a really important place to start, just to understand things kind of conceptually. The graph really helps. So let's say that this graph represents the velocity of a particle. And our horizontal axis is the time axis. And I want to know how far did it travel. So this graph represents how fast and in what direction it's going, right? It's traveling to the right here, it's traveling to the left when it's below. And I want to know how far it went. So there's two important questions to look at. First is displacement. And our definition of displacement that I want you to be really comfortable with is net change in position. Where are you in location to where you started? So displacement is just simply equal to the integral from A to B of velocity, right? If the integral represents the net change in value of the antiderivative of velocity is position, then displacement will tell me, or integral of velocity will tell me displacement, net change in position. By the fundamental theorem of calculus, I could rewrite this integral as the position at time B minus the position at time A, net change in position. So where are you at in comparison to where you started? I would just simply integrate. So that would take this area of this trapezoid right here, subtract the area of this triangle that's below, and that would give you displacement. Very simple. So it's simple to do algebraically here, simple to do graphically as well. So the other question is, what about how far it went? So total distance traveled. You know, not just where am I at compared to where I started, but how far did I actually go? And this is really easy to see on the graph. In order to figure out how far you went, you need to take how much you traveled to the right and take this region that's below and make it positive. So you're going to make all of your areas positive and do a total area to get total distance. Algebraically, this would be the integral from A to B of the absolute value of velocity. Now, doing this in a calculator is simple. You can just type this in the way it's written. Doing it without a calculator requires you to do a little bit of work. We need to figure out first, when does it stop? So let's say that this time is time C. So if I were to evaluate this by hand, I would need to take the integral from A to C. That would give me my change in position up until that point where I change in direction. And then I would subtract the integral from C to B of velocity. So subtracting that negative part will make it positive, and this will accomplish the same thing that the absolute value integral does right here. So if you're asked to do this by hand, this is the way to go. Figure out first where it stops, and then determine from there which parts are positive and which parts are negative. Hopefully some analysis in that problem has led you to that point already. Calculator version is very simple. Graph version, even simpler. All right, let's dive a little bit deeper now. We got a nice little overview here, but let's look a little further at some other integral ideas with motion. So things that we've written so far. The integral from A to B of velocity is the net change in position, which is the displacement. The integral from A to B of the absolute value of velocity is my total distance traveled. So what about some other stuff? Well, we can use the fundamental theorem of calculus to do more with this. So let me give you an example. Suppose the position of some particle at time 0 is 2 in your given velocity. So you're given an equation for velocity. Oops, don't need the dt there. Thinking a couple steps ahead, given v of t. And you're asked for find the position at t equals 3. So in order to do this, we're going to apply the fundamental theorem of calculus. We're going to take my initial starting position, which is 2. And we're going to add that to the net change in position from time 0 to time 3 of so the integral of the velocity from 0 to 3. Why does this work? You start at position 2. This integral represents the change in position from time 3, from time 0 to time 3. So if I add x of 0, it's going to cancel out this minus x of 0. It's just going to give you x of 3. So that's the way that we would solve that problem pretty quickly. Now, you could also anti-derive plus c, add c, and then solve for c, and then work it that way. But I'm going to say that. What if I said find the position at t equals, not at t equals, let's say at any time t. So this would be creating an equation to represent the position. So in this case, I would want to take the antiderivative plus c and then solve for c using the initial condition. So this is much more differential equations-esque when you do that. You could use the fundamental theorem of calculus version. We could say 2 plus the integral from 0 to some time t of v of x dx. This would work as well if I wanted to work it that way. But I think that most of us would like this version here, where we add c and then solve for it to get the q version. We can continue to dive deeper with this too, but I think most of this just leans on your conceptual understanding. So if I imagine we talked about the integral of velocity, what about the integral of acceleration? This would be equal to the net change in velocity, right? Because it's the net change of the antiderivative, which would be v. You could use this in the same way. If I gave you a velocity at a certain time and asked you for a velocity at another time, you could utilize the fundamental theorem of calculus the same way we did the new position problem. So a lot of different ways that this can go. And really, it's so important just to understand the full overview, the full concept of this topic. Why does it work using the fundamental theorem of calculus? What does it look like graphically, which we talked about at the beginning? And how can I use it in a table we've seen with Riemann sums and other things? So it's a much broader concept that we're kind of honing in on one aspect of it. But it's a very important aspect, and it definitely deserved its own video for this series. So definitely take some time to dive in. Make sure you really get this and understand each part of this. Understand it with this graph, and then algebraically, and then how could you work with it in the table. Okay, guys, thanks for watching, and I will see you next time.